Hello, let us start chapter 5, module 7. In this module, our target basically to discuss the prerequisites to prove Ascoli-Argela theorem. We know that Bolzano-Weierstrass theorem says that closed and bounded subsets of Rn are compact. Now, if we consider a topological space X and all continuous functions from X to Rn, we can consider the submetric on Cx if X has been considered compact sets. Now, this is a question to us whether under submetric Cxrn has some property analogous to Bolzano-Weierstrass theorem. That means whether we can say that any closed and bounded subset of Cxrn is compact. This is not true in general. We need some extra condition to say some kind of statement. To prove Ascoli-Argela theorem, which says about this, we need some basic prerequisites. In this module, basically we discuss about these prerequisites. So, let us go to slide presentation. We have already discussed about totally bounded metric spaces. In fact, a metric space will be called totally bounded if it has a finite epsilon net, where by a epsilon net we mean a subset of that metric space such that the open balls centered at the points of that subset of radius epsilon covers X. So, a metric space is totally bounded if it has a finite epsilon net. Not every bounded set in arbitrary metric space is totally bounded. For example, if we consider discrete metric space, then it is bounded, but it is not totally bounded. For if we take epsilon is equal to half, we can't find any finite epsilon net. So, discrete metric spaces are bounded, but not totally bounded. Now, it can be proved that a metric space is compact if and only if it is complete and totally bounded. Let us first prove that if X is compact, then it is complete and totally bounded. To prove the completeness, let us consider a sequence xn in capital X, which is a Cauchy sequence. Now, since X is compact and in metric space every compact space is sequentially compact, therefore, this Cauchy sequence has a convergent subsequence. Now, if a Cauchy sequence has a convergent subsequence, we know that the Cauchy sequence itself becomes convergent. This proves that in compact metric space every Cauchy sequence is convergent. So, every compact metric space is complete. Now, To prove the total boundedness, let us take a positive real number epsilon and consider the open balls Bx epsilon centered at x. Then the collection Bx epsilon such that x belongs to capital X is a cover of x. Since x is compact, we have a finite subcover of this open cover, say x1, x2, xk. Then this finite set x1, x2, xk becomes a finite epsilon net. Therefore, capital X is totally bounded. The converse part is much more difficult. Let X be a complete and totally bounded metric space. We want to prove that capital X is sequentially compact. Since in metric spaces compactness and sequential compactness are equivalent, it will sufficient to prove that the metric space is sequentially compact. Now, to prove that capital X is sequentially compact, let us consider a sequence Xn in capital X. We have to find a convergent subsequence of the sequence Xn. Now, we claim that there exists a subsequence Xn that is Cauchy, so that it necessarily converges. Let us take an open cover of finitely many open balls of radius 1. Now, since this consists of finitely open balls, at least one of these balls contains infinitely many points from the sequence Xn. Let us rename this open ball as B1. Now, let us set J1 is equal to all those n belongs to n such that Xn is contained in B1. Now, again let us cover X by finitely many open balls of radius half. We can do this as X is compact. Because J1 is infinite, at least one of these balls must contain infinitely many Xn, where n comes from J1. Let us rename this open ball as B2 and choose J2 is equal to all n belongs to capital N such that Xn belongs to B2 and n is in J1. In general, using induction, we can get an infinite set Jk of positive integers, and we can choose Jk plus 1 to be an infinite subset of Jk such that there is a ball Bk plus 1 of radius 1 by k plus 1 that contains Xn for all n belongs to Jk plus 1. That means when we have already prepared J1, J2, Jk, then as above we can prepare jk plus 1. So, jk plus 1 contains all those members of the sequence xn such that n belongs to jk and xn belongs to bk plus 1. Now, let us choose n1 belongs to j1. Given nk, let us choose nk plus 1 belongs to jk plus 1 such that nk plus 1 strictly greater than nk. In fact, we can do this as jk plus 1 is an infinite set. Now, for I and j both greater than k, the indices ni and nj both belongs to jk, as j1 j2 is a nested sequence of sets. Therefore, for all ij greater or equal to k, the points xni and xnj are contained in a ball bk of radius 1 by k. This shows that xni is a Cauchy sequence, and therefore we have that xni is convergent. This completes the proof. We have already mentioned that in this chapter we shall prepare some prerequisites of Ascola-Argeli theorem, which investigate whether CXRN has behavior like Rn. That means whether we can say a closed and bounded subset in CXRN with submetric is compact or not. We have mentioned that we need some extra properties. To make prerequisites of this theorem, we have proved that a topological space X is compact if and only if it is complete and totally bounded. As byproducts, we have some more results which we will discuss in this module. Let us pass to slide presentation. The following property is an interesting one. Let A be a subspace of a complete metric space, then A bar, that means closure of A, is compact if and only if A is totally bounded. For the proof, let A be a subset of a complete metric space X such that closure of A is compact. We have to show that A is totally bounded. Now, since X is complete, therefore closure of A is complete. Hence, we have that closure of A is complete and closure of A is compact. So, by our previous theorem, closure of A should be totally bounded, and therefore A being subset of closure of A is also totally bounded. Now, for the converse part, let A be totally bounded. We have to prove that closure of A is compact. Since X is complete metric space, therefore closure of A is complete. Now A is given totally bounded. It can be proved easily that closure of A is also totally bounded. Therefore, we have that closure of A is both complete and totally bounded, and therefore it is compact. Now, we prove that a product theorem, if Xn is a collection of metrizable spaces with metric Dn, then let us consider the metric dxy is equal to supremum of di bar xi by I, where di bar is the bounded version of the metric di. Then in the product space of Xn, capital D is a metric. It can be proved that if X is totally bounded under the metric D, then each of Xn is totally bounded under Dn. In fact, let us choose an epsilon greater than 0, then we can find a finite set of points in the product such that finite epsilon ball covers the product. Now, if we take the projections of these finite points, then we get a finite epsilon net in the factor space. Thus, we can say that if product is totally bounded, then each factor space is totally bounded. In that way, we can conclude that without using Tychonoff product theorem, that countable product of compact metrizable space is compact. Now, let us prove another property. Let capital X be a metric space, and suppose that for some epsilon greater than 0, every epsilon ball in X has compact closure, then capital X is complete. To prove that, let us observe that if we take a Cauchy sequence that should be contained in some epsilon ball, and epsilon ball being compact, we can find some convergent subsequence and the Cauchy sequence becomes convergent. This completes the proof. Next, we like to define topological completeness. A topological space X is said to be topologically complete if there exists a metric, say D, for the topological space X, relative to which X is a complete metric space. It can be proved that closed subspace of topologically complete metric space is topologically complete. To prove this, let X be a topologically complete metric space and let capital Y be a closed subspace of that topologically complete metric space. Now, X is topologically complete metric space, that means that there exists a metric D such that the topology generated by that metric D is equal with the topology of X, and since X is topology complete, therefore with respect to this metric D, X is complete. Now, as Y is closed subspace of X, therefore Y also becomes complete with respect to the metric D when D restricted on Y. Therefore, Y is a topological space and we have a new metric D restricted on Y with respect to which Y is complete. Therefore, Y becomes topologically complete. Hence, we conclude that closed subspace of topologically complete metric spaces are topologically complete. The following results can be proved easily. Open subspace of topologically complete spaces is topologically complete. The following also can be proved that if A is a G delta set in a topologically complete space, then A is topologically complete. We know that a subset of a metric space X is called G delta if it can be expressed as countable intersection of open sets. Therefore, these results implies that the space of irrationals in R is topologically complete because the space of irrationals is a Z delta set in R. We end this module with the very much important theorem. Any continuous mapping of a compact metric space into a metric space is uniformly continuous. In fact, one version of this theorem we know from elementary calculus. We know that every continuous function defined on a closed unit interval is uniformly continuous. This theorem is a generalization of that theorem. To prove this, let F be a continuous mapping of a compact metric space X into another metric space Y. Now, for each X belongs to capital X, consider its image f of X and the open sphere B of fx epsilon by 2. Since f is continuous, the inverse image of each of these open spheres is an open subset of X, and the class of all such inverse images is an open cover of capital X. Since capital X is compact, this open cover has a Lebesgue number, say delta. If X and Y are any two points in capital X for which dxy less than, then the set containing points X and Y is a set with diameter less than delta. So, both point belongs to the inverse image of some one of the above open spheres. Both fx and fy belongs to one of these open sphere, and therefore we have rho of fx fy less than epsilon, which shows that f is indeed uniformly continuous. So basically in this module we have proved that a metric space X is compact if and only if it is complete and totally bounded. This will be required in proving Escola-Argeli theorem. With this we end this module. Let us pass to the next module.